Hello everyone and welcome to EECS 2021. This is going to be the first session. Alright, so we're going to go over the tools and processes that we're going to use in this course, and there'll be other sessions in which we talk about number processing and decimal with reverse Polish notation, etc. We'll talk about digital logic, instructions, etc. But that's way down the road. We're going to start off with the overview. Okay, so first of all, who am I? My name is Dr. James Andrew Smith. I'm a professional engineer and a associate lecturer here in the Lassonde School of Engineering. My office is located in the Lassonde Research Center at 4751 Kiel, so it's across campus. My office hours will be to be discussed, and you can contact me using the eecs2021.fall2022gmail.com email address. You can find me online at those web addresses and on Twitter at that particular handle. I'm a dedicated teaching professor, and I also do a little bit of research on the side in robotics and embedded systems. Okay, so what is 2021? It's basically a course about how computers work. It's an introduction to computer organization, instruction set architecture covering assembly language, machine language, encoding, addressing modes, data paths, pipelining, memory segments, and memory hierarchy. So basically it's how do the internals of chips work. We're going to have the equivalent of 3 lecture hours a week and 3 lab hours per week. It's offered as a blended course, so the lecture hours are more asynchronous, and we have additional office hours to cover what would otherwise be a regular in-person lecture. The labs will be done in large part online, and we'll be discussing the details later on. Okay, so how is the 2021 course this year different in fall of 2022? Well, effectively, we have made it into what's referred to as blended, which means it's mostly online. It's designed to be classes effectively all online and labs mostly online. The assumption is that you're going to be active in your learning in a way that was very similar to what you did in EECS 1011 and 1021. All of the content will be delivered over the eClass page, a lot of it pulled from YouTube videos that are linked from eClass, so you can watch the YouTube videos, you can watch them interactively as well on eClass. Because of a scheduling conflict, the lecture time slot won't be held, and we will find alternative synchronous sessions for optional discussions. Zoom sessions will be done with myself and with TAs, and we will provide you with multiple venues for discussion and opportunities for answering your questions. The grading is going to be done based on proficiency-based grading, which you've seen in both 1011 and 1021. There is no final exam, there is no midterm, there are no tests, there are no quizzes. Basically, the idea is that if you get all of the work done in this course as scheduled, as displayed, as presented to you, you'll get a B+. If you want to exceed that, then you can work on an extra special project that is similar to what was done in 1011 and 1021. And in all of that together, the expectation is that you're going to be tracking your progress, and when things get difficult, you come and talk to either the TAs or myself so that we can figure out how to resolve those difficulties. Okay, this course has five major course learning outcomes. By the end of the semester, you, the student, are expected to be able to do these 5 things. First, you're expected to be able to translate high-level code to assembly language and machine code. That means going from C to assembly and then down to machine code. The next one, represent the data in machine-readable form and describe how it is stored and manipulated in the CPU. We're going to show you how data flows inside of the microprocessor. Third, you're going to be expected to be able to synthesize hardware of increasing complexity from logic gates to a simple CPU using a hardware description language, in this case, Verilog. Fourth, by the end of the semester, you will be expected to be able to evaluate computer performance and compare performance on different architectures and designs. Fifth, by the end of the semester, you will be expected to be able to describe and critique the CPU operation and pipelining. Usage and copyright. It's important to point out that the content for this course was developed by a number of different people. including myself, but also some of the people that you see listed right here. The intellectual property for these people is to be respected, and that means that you can use the material in the context of this course because you have permission to do so, but you do not have permission to upload content or to share content from this course with others outside of the course. You don't have permission to upload it to Course Hero and other places as well. So please respect the copyright of the original creator. If you have questions or if you would like to use some of that material for a particular purpose, please feel free to come and discuss it with myself or some of the other authors. All right, let's get into microprocessors. What are the basic operations inside of a microprocessor? Well, what's important to point out is that the black box that you normally see with little pins, little metal pins that come and stick out of it, there are circuits inside of it that are controlled by the software that is written for that particular chip. Inside of that chip, there are things like registers. There are things like the arithmetic logic unit. There are things like control circuitry that connect different components together. And these things come together in a very agreed upon kind of way in order to make sure that the behavior of the processor is predictable. Okay? Now, the microprocessor is a combination of electronics that come to life if you put the right kind of electrical signals through it, but you're not controlling those electrical signals directly. You're getting these signals from the software that you write. And typically, you're writing that software in a language like C or C++ or MATLAB or Java or Python. In this course, however, we're going to go under the hood. We're going to talk about what happens after you've written that code in a high-level language, what happens when it gets converted or transitioned into or translated into something called assembler, which is closer to what is what the machine actually speaks. And then we're going to talk about how that assembler gets converted once again into what a lot of people would call machine language. The ones and zeros you see in movies and things like that. Well, what are those ones and zeros? These ones and zeros, the machine language, is really what eventually drives the circuitry, the combination of electronics that actually make things move and work in the chip. Okay, and this course is going to be about knowing the right combinations of software and hardware to do useful things. We're going to learn how real-world engineers work with microprocessors, which means that we're going to be doing things in high-level languages like C, and then we're going to show you how that gets converted into assembler and how we can basically optimize things that are in C into a better form in assembler. And we're going to show you how to debug software written in both C and assembler, that interaction between C and assembler. Because in the real world, when people want to have optimized software, when they want it to work exactly as specified, they are often combining both a high-level language and a low-level language like assembler together. So let's talk about this code translation hierarchy. Typically, somebody produces a program in a high-level language like C or Java or one of these other languages. That program is then converted using a compiler into assembly code. You normally don't see that assembly code. Okay, that assembly code is then run through an assembler, which then makes object code. That object code is linked with library routines into an executable file, which is then loaded into the memory of the microprocessor. You play a vital role in all of this process. You are typically writing software in C or maybe even in assembler. It then gets converted into that executable program that we talked about in the previous slide and runs through a programmer or a debugger into the microprocessor or microcontroller, where it then interacts with things like EKGs or alert lights or ventilator pumps, etc. In practice, what we're seeing is that you'll start with a high-level language program written in C. Maybe there'll be header files as well. You'll have GCC or some other compiler create an assembly file. It gets run through the assembler into objectfiles.o files, which then get linked together using the linker, like LD, which then creates an executable or ELF or hex file with a combination of object files, the libraries, and that gets run through what you see right here is a debugger and into a board from there. All right, let's move on to number processing, decimal and reverse Polish notation.